excited to introduce Shuichi Hirahara, who in the last few years has obtained a sequence of results on average case complexity, which really changed the picture of what we thought was possible. And he will tell us about it today. So please, Shuichi, go ahead.
Thank you so much for inviting me. It's a great pleasure to present this talk. So today I'm going to talk about the relationship between average case complexity and metacompressing. So I would like to start with a very broad overview on complexity theory and cryptography. And in particular, I would like to explain Impagrat's fibers, and then I will explain a recent progress on the question of excluding Heuristics. Let's pretend for a moment that our world is a world where P is equal to NP. Then it's quite fantastic in the sense that if P is equal to NP, then you can solve every problem in NP quite efficiently. There are a lot of problems in NP that we would like to solve efficiently. For example, if P is equal to NP, we can do automated theorem proving in polynomial time. So this is quite fantastic if P is equal to NP, but at the same time, it's a bad thing for us. Because if we consider any public key crypto system, we can break it. The security can be broken if P is equal to NP. And recently, the value of Bitcoin is increasing. And if P is equal to NP, then the value becomes 0. Because in the system of Bitcoin, we use public key crypto system. So the message of this is that if P is equal to NP, then our society must be completely different from what we live in now. So in order for our society to continue as it is, we need to prove that P is different from NP. But even if P is different from NP, we don't know whether we can construct a public key crypto system or not. And today's talk is about filling the gap between P versus NP and cryptography. And this gap between P versus NP conjecture and cryptography was clearly explained by the celebrated work of Russell Impagratto. So Russell Impagratto proposed 5 possible worlds that are consistent with our current knowledge on cryptography and complexity theory. So here are 5 worlds from algorithmic up to cryptomania. For example, algorithmic is a world where P is equal to NP. In this world, it's impossible to construct a secure crypto system. And the rest of the world corresponds to a world where P is different from NP, and it is further classified in this way. For example, the topmost world is called cryptomania, and this is a world where there is a secure public key crypto system. Most of us believe that our world corresponds to cryptomania, but we don't know whether it is true or not. There are other worlds. For example, there is a world called pestilent. This is the worst possible world in the sense that in this world, it's impossible to construct a secure crypto system, and at the same time, you can't solve NP efficiently on average. And there is a world called min crypto, which is a world where it's impossible to construct a public key crypto system, but you can do minimal crypto system in the sense that you can construct a secret key crypto system. Finally, there is a world called Heuristics. This is a world where heuristics are quite efficient in the sense that there are quite efficient polynomial time heuristics that can solve NP on average. But at the same time, it means that it's impossible to construct a crypto system. So these are 5 possible worlds which are consistent with our current knowledge. And we know that exactly one of them corresponds to our world, but currently we don't know which world corresponds to our world. The ultimate goal of complexity theory and cryptography is to decide which world corresponds to our world. In particular, most of us believe that our world corresponds to cryptomania. So in order by resolving that conjecture, eventually we would like to construct a public key crypto system and we would like to make our society more reliable and more secure. So these are quite important open questions. Now, what we know about this? Well, in some sense, we have just a trivial implication. Namely, if we have a public key crypto system, we can construct a secure key crypto system. And if you have a secret key crypto system, then we can show that NP is hard on average. And if NP is hard on average, then NP is hard in the worst case. Now, the converse direction of these implications correspond to the central open questions in the theory of complexity theory and cryptography. For example, the bottom blue implication corresponds to the open question of proving P is different from NP. And if we can prove this, we can show that our world is not algorithmic. In other words, we can exclude algorithmic from 5 possible worlds. Similarly, if we can prove the second blue implication, we can exclude Heuristics from 5 possible worlds. In general, if we can prove one blue implication, we can exclude one possible world. And finally, if we can prove all the 4 implications, we can conclude that our world is cryptomania, and we can construct a truly secure public key crypto system. But these are quite central open questions in the theory of complexity theory and cryptography. So there are a lot of work that explain why standard proof techniques cannot resolve these open questions. For example, if we want to solve P versus NP conjecture, we need to develop new proof techniques that simultaneously overcome relativization, algebraization, natural proof barriers. So standard proof techniques that do not work, and we need to develop new proof techniques. Similarly, in order to exclude Heuristics from 5 possible worlds, there are 3 barrier results: relativization barrier and the limits of Blackbox reduction and the impossibility of hardness application. So in order to make progress, it's very important to develop new proof techniques that are not subject to these barriers. Fortunately, there is a recent new emerging paradigm which we call metacompressing, and I'm going to talk about what metacompressing are. So in one sentence, metacompressing is the complexity of problems asking for complexity. Let me give you one representative example of metacomputational problem, which is called MINCATI. This stands for minimum time-bounded Kolmogorov complexity problem. And this is a problem of computing time-bounded Kolmogorov complexity intuitively. More specifically, you are given a binary string X, and you are asked to compute the minimum program that prints X efficiently. In other words, this problem asks for the complexity of generating input X. So in this sense, this is called metacomputational problems. By considering this metacomputational problem, 3 years ago, we were able to show that for this problem, worst case and average case complexities of MINCATI are equivalent. More specifically, we can show that MINCATI is hard on average with respect to the uniform distribution if and only if gap MINCATI is hard in the worst case. Gap MINCATI is an approximation version of MINCATI. I will explain the definition later, but what's important about this is that this goes beyond the limits of Blackbox reduction. Briefly, limits of Blackbox reduction, which was presented by Bogdan Trevisan, states the following. If you have a worst case to average case reduction in NP, there are limits saying that if you have a Blackbox reduction, the problem must be in NP/poly intersection of co-NP/poly. And there is a conjecture by Rudy stating that gap MINCATI should not be in the problem in co-NP/poly. So in this sense, this is the first result that goes beyond the limits. I will explain the detail of limits of black box reduction later, but before that, let me explain recent progress on this research line. There has been a long-standing open about worst case to average case connection. There is a complexity class called UP, which is a subclass of NP. This is a class that contains, for example, integer factorization. Now, let's assume that UP is exponentially hard in the worst case. Can we show that NP is hard on average? This has been a long-standing open question on the relationship between worst case and average case complexity. And the reason is that there are several excuses for this long-standing open question. For example, if we want to resolve this open question, we can't use a black box reduction to prove this. Similarly, there is a standard proof technique called hardness amplification procedure, but you can't use the hardness amplification procedure to prove this implication. It's not clear whether we can apply relativization barrier to this setting, but in order to resolve this open question, we need to use a proof techniques that simultaneously overcome these two barrier results.
Shuichi, so you said the factoring is an example, or integer factorization is an example of a UP problem, but integer factorization does have like 2 to the little o(n) time algorithms. So is there sort of some other natural problem to which you can apply this assumption that would give you hard on average NP problems?
Yeah, actually, that's a very good question, and I'm not aware of a natural problem that satisfies this assumption, unfortunately. Here, I should emphasize that n denotes the input length of as a binary input. So integer factorization can be solved in sub-exponential time in this sense. So it's an interesting open question to find a natural assumption that satisfies this. Yeah, thank you for the question. Anyway, we were able to prove this implication, and yeah. So we were able to show that if UP requires the time compressive 2 to the little order n, then we can show that NP is hard on average. So this statement doesn't refer to metacompressing at all, but what's interesting is that it relies on metacomputational proof techniques. So I would like to explain why metacompressing are useful to studying average case complexity in a later part of this talk. But before that, let me try to explain some more recent progress. This result actually shows that if UP requires a time compressive 2 to the order n by log n, which is a quite weird time complexity, we can show that NP is hard on average. Now, eventually, we would like to weaken the assumption to NP, the assumption that NP is different from NP, which would exclude heuristical. Now, let's consider whether we can slightly improve this. Namely, can we improve this time bound to slightly to 2 to the little order n by log n? For this open question, of course, we have limits of black box reduction and the impossibility of hardness amplification. But recently, it turned out that there is a relativization barrier as well, which we showed in the joint work with Michito Nanashima. So the message of this is that if we want to go further, we need to develop new proof techniques that also overcome limits of relativization proof techniques. So somehow this weird time complexity turned out to be somewhat optimal in some sense. But there is a way to bypass relativization barrier, and we can still make some progress by considering fine-grained 5-world. So if we usually consider in particular to 5-world, we usually talk about polynomial time adversary as a default setting. So if we say that there is a public key crypto system, this is a mathematical statement saying that there is a secure public key crypto secure against polynomial time adversary. But there is a notion called fine-grained public key crypto system, which is secure against quasi-linear time adversary. And we can draw a similar diagram which is similar to the left, the standard 5 possible worlds. And in this diagram, we showed that if UP requires a time compressive 2 to the order n by log n, then we showed that NP is hard on average in the usual sense. If we are satisfied with a weaker conclusion that NP is slightly hard on average, we were able to show that the assumption can be weakened. Namely, if UP requires a time compressive 2 to the order square root n log n, then in a joint work with Rizhi Chen and Nikon Pfeffer, we were able to show that NP is slightly on average. So this result doesn't overcome relativization barrier, but this shows how to bypass relativization barrier in a sense. So we can still hope to make progress on this difficult question. So next, I would like to explain limits of black box reduction. Is there any question before that? Okay.
No, you can go ahead.
Okay, let me explain the some details of limits of black box reduction. Well, before that, let me quickly remind you some of basic standard compressed classes. Here you have P and NP and co-NP, and between that, in between you have a UP, which stands for ambiguous polynomial time, which is a class of problems solvable by a non-deterministic polynomial time machine that has at most one accepting path for every input. You can understand the compressive UP as a compressive injective one-way function. There is a nice characterization saying that UP is different from P if and only if there is a one-to-one one-way function that is hard to invert in the worst case. There is a generalization of NP, which is called PH, which stands for polynomial time hierarchy, and above that you have P space. Now let me explain black box reduction. Black box reduction are quite powerful proof techniques in the context of worst case to average case reduction. And in fact, we can prove several connections between worst case compressed and average case compressed NP. For example, one of the celebrated work by Aitai shows that if the shortest vector problem cannot be approximate in the worst case, then he shows that NP is hard on average. Similarly, if we can reduce statistical zero knowledge to distributional NP, in the sense that if statistical zero knowledge is not in the worst case, then distributional NP is hard in the sense that it's not in average P. There is also a simple padding trick which you can do, and you can actually prove that if NP requires a time compressive 2 to the big O over n, then you can show that NP is hard on average. And these are actually proved by black box reductions. What do I mean by black box reduction? Well, this is just a standard reductions. Namely, if we want to show that some computational problem is harder than easier than the other, we consider an oracle that solves some problem. For example, in some problem in distributional NP, and we would like to solve the problem on every input. For example, in the case of statistical zero knowledge, we can construct a reduction such that for every oracle that solves some distributional NP problem, the reduction given oracle access to A, it outputs the correct answer for every input. In this way, we can show the worst case to average case reduction. So this is a standard reduction, but what I'd like to emphasize is that black box reduction doesn't impose any efficiency requirement on the oracle. And when we say a reduction is non-black box, we say that we assume that we mean that the reduction might fail if the reduction is inefficient. So this is the difference between black box reduction and the non-black box reduction. Now, the limits of black box reduction, which were established by Feigenbaum-Fortner and Bogdan and Trevisan, shows the following. Let's consider any language, any problem, which is outside NP/poly intersect co-NP/poly. Then you cannot construct any non-adaptive black box reduction from L to distribution of NP. In other words, non-black box reductions are too strong notion to be useful if you want to get worst case to average case connections for NP outside co-NP/poly. So this is a figure. Here you have NP/poly intersect co-NP/poly, and it is conjectured that gap linkage is outside the limit. So in order to show worst case to average case connection for any problem outside this limit, we need to use non-black box reductions or adaptive reductions. It can be the case that adaptive reductions are helpful in this context, but currently we don't know any reduction that goes beyond the limits of the black box reduction. Instead, I'm going to show how to use non-black box reduction, and in particular, I'm going to explain why by using metacompressing, we can develop non-black box proof techniques. And I'm going to explain how we can exploit the efficiency of an oracle. Now, let me state our result, and I'd like to explain the details of the proof techniques and metacompressing. So here is there are three main results in the stock paper. The first result is what we already talked. So it states that if UP requires a time compressive 2 to the order n by log n, then NP is hard on average. What I should emphasize that the n denotes the length of inputs, which is encoded as binary strings. Similarly, we can prove that if pH requires a time complexity of 2 to the order n log n, and then we can show that the distribution of pH is hard on average. And we can also prove that there is a worst case to average case connection for LP, in the sense that if NP requires a time complexity of 2 to the order n log n, then we can show that LP is hard on average in a slightly stronger sense, slightly weak sense. Here, average sub PP denotes P computable average case polynomial time, which interpolates worst case complexity and average case complexity. Namely, average sub PP is a subclass of average case polynomial time algorithms, and this is a class of distributional problems that can be solvable by average case polynomial time, whose running time can be estimated in a sense. More specifically, this is a class of problem that can be solved by average case polynomial time, and we require that there is an average case running time, which upper bounds the running time of the algorithm, and the upper bound of the running time can be computed in worst case polynomial time. So this is a stronger notion than the usual average case polynomial time, but for this stronger notion, we can establish worst case to average case connection for NP. Of course, the weakness is that NP requires its worst case complexity. But let me quickly mention that we can prove a slightly stronger statement. For example, you might wonder what the hard distributions are. Actually, we can take a quite simple hard distribution. So the hard distribution we can consider is the uniform distribution U and the tally distribution, which is denoted by T. So here, tally distribution is a quite simple distribution, which is supported only on a unary input. We can prove that for such a distribution, there is a hard problem in NP that is hard on average. And let me also mention that instead of errorless heuristic scheme or average case polynomial time, we can also prove a hardness for one-sided error heuristics. Namely, this corresponds to the hardness of refutation. And we can also prove that the success probability is very tiny. Namely, we can show that there is no polynomial time algorithm that succeeds with probability n to the minus c, where c is any constant. Let me also quickly mention that instead of UP, we can consider a slight generalization, which we call size verifiable NP. And this is related to the complexity of imparting a size verifiable normal function in the worst case. Anyway, let's talk about how we can prove such worst case to average case reduction that goes beyond the limits of standard proof techniques. So the proof techniques is based on metacompressing. But before explaining metacompressing, I needed to explain the time-bounded Kolmogorov compressing. T time-bounded Kolmogorov compressing of X is usually denoted by K superscript T of X, and this is defined as the length of a shortest program that prints X in T steps. Let me give you 3 simple examples. For example, let's consider the complexity of all 0 string. Then, in order to upper bound this the Kolmogorov compressing of this string, we can consider a simple program saying that print 0 n times. Now, by considering this program, the length of this program is at the most order 1 plus the binary representation of n, which costs you log n. So the Kolmogorov compressing is at most log n plus order 1. Similarly, if you consider the trivial algorithm that print x, you can show that the time-bound Kolmogorov compressing of x is always at the most the length of input x. And by using a simple counting argument, we can also show that there is a high complexity string. And in particular, if you pick a uniformly at random x, we can show that even if you have a time-bounded Kolmogorov compressing, the time-bound Kolmogorov compressing is at least n-2 with high probability. So this is the notion of time-bounded Kolmogorov compressing. Now let's consider metacompressing, which is the complexity of compressing. There are several examples of metacomputational problems such as MCSP, MKTP, and MinKT. And in this talk, I'm mainly considering MinKT, which was introduced by Kerry Ko. This is a problem of computing the time-bounded Kolmogorov compressing. More specifically, this is the definition of T time-bounded Kolmogorov compressing, and MinKT is defined as follows. The input to the MinKT consists of X, which is an input, as well as a time parameter T, as well as a size parameter S. These are encoded as a unary string, and the problem is to decide whether T time-bounded Kolmogorov compressing of X is at most S or not. So informally, this is the problem of computing the T time-bounded Kolmogorov compressing of X. This is called MinKT. And let me quickly mention that there is an additive approximation version, which is called gap MinKT. This is an order log n additive approximation version of min-kt. And more formally, this is defined as a promise problem, which consists of yes instances and no instances. Promise problem is a problem of accepting every input from yes instances and rejecting every no instances. And the yes instances of gap min-kt consists of the same input to the min-kt, and no instances consists of inputs whose hormonal complexity is slightly larger than the size parameter by additive factor of order log n. And here P is some polynomial, and we say that gap min-kt is in P if there is some polynomial that can distinguish these two sets. Anyway, intuitively, this is just an order log n additive approximation version of min-kt. There is a slightly generalized version of min-kt, which is usually denoted by min-kt to the A, which is an A oracle version of min-kt. So the only difference between min-kt and min-kt to the A is that in this problem, we are going to ask A oracle T time-bounded hormonal complexity. So what's the A oracle time-bounded hormonal complexity? Well, here, the problem you are minimizing is given access to oracle access to A. And this is denoted by KT superscript A. So min-kt to A is a problem of asking the minimum program that prints X in T steps, given oracle access to A. You might wonder that A is reducible to min-kt to the A, but currently we don't know whether it is true or not. And it's easy to see that this is a problem in NP. Namely, in general, min-kt to the A is a problem in NP to the A. But actually, it's a long-standing open question whether we can prove NP, min-kt is NP hard or not. In fact, even if we have a pH oracle, we don't know whether it is NP hard or not. So this is the metacomputational problem we are going to consider. Now, why is it important to consider metacompressing? Well, actually, we can exactly characterize average case complexity of pH by using the notion of metacompressing in the following sense. Distributional pH is in average P, namely pH is easy on average if and only if gap min-kt to the pH is in P. This statement means that for every oracle A in pH, gap min-kt to the A can be solved in the worst case. So gap min-kt to the A is an order log n additive approximation version of min-kt to the A. So this characterization shows that we can understand average case complexity through the notion of metacompressing. What's interesting about this characterization is that as a corollary, we can get a new proof technique of analyzing average case complexity that uses metacompressing. Let me give you an example. For example, by using this characterization, we can prove that there is an average case hardness application for pH. The statement itself isn't so important, but the proof is more interesting. And the proof is given by going through the notion of worst case metacompressing. Namely, here I'm writing a statement about the average case complexity on the left, and I'm writing a statement about worst case metacompressity on the right. And the proof can be proved by going through the notion of worst case metacompressity in this way. You might wonder that this is a detour, but intuitively, the reason why it's this makes it easier to analyze is that in general, if you compare worst case complexity and average case complexity, it's easier to analyze worst case complexity than average case complexity. So at a very high level, the reason why this characterization is useful is that it makes it possible to analyze average case complexity by the notion of worst case complexity. Now let's explain how we can prove the worst case complexity, the connection between the worst case complexity and average case complexity. For the purpose of the talk, I'm going to explain the proof of the statement that if NP requires a time complexity of 2 to the order n by log n, then I'm going to show you how to prove pH is hard on average. The proof looks like quite similar to the previous diagram. So on the left, I'm going to write a statement about the average case complexity, and the proof somehow goes through the notion of worst case metacompressity in this way. So there is a key notion which we call universal heuristic scheme. So let me explain what the universal heuristic schemes are. So before explaining the definition of universal heuristic scheme, let me mention that why we call it universal. So universal heuristic scheme is a kind of worst case metacompressity notion, but this satisfies the following universality. So we can prove the following statement are equivalent for every problem L. So the first statement says that there is a universal heuristic scheme for L. And the second statement states that L can be solved on average in the sense of a p-computative average case polynomial time with respect to every polynomial time sample of distribution. So universal heuristic scheme is just one algorithm, but we can show that it is a good heuristic for every polynomial time sample of distribution. That's why we call it universal heuristic scheme. Now let's give a definition of a universal heuristic scheme. Well, in order to explain the definition of universal heuristic scheme, let's explain the fundamental notion of computational depth. Computational depth is a very simple notion, but it's a quite powerful notion, which is defined as follows. Computational depth, CD suffix T of X, is defined as the difference between T time-bounded Kolmogorov complexity of X and the time-unbounded Kolmogorov complexity of X. And we can consider a slightly generalized version of computational depth, which we call TS, time-bounded computational depth, which is denoted by CD suffix T and S. This is just defined as the difference between T time-bounded Kolmogorov complexity of X minus S time-bounded Kolmogorov complexity of X. So that's the definition. Now we can define the universal heuristic scheme. So we say that an algorithm A is a universal heuristic scheme for L if there is some polynomial P that satisfies the following two conditions. The first condition says that the universal heuristic scheme outputs the correct answer always for every input. And the universal heuristic scheme takes input X as well as a time parameter T. And you must output the correct answer always. And the question is the running time. We require that the running time of the universal heuristic scheme is proportional to the time computational depth. Namely, it must be 2 to the order of computational depth of the input X plus log of T, where T is a time parameter. So in other words, the time complexity of universal heuristic scheme is characterized by the time-bounded computational depth. And let me emphasize that this is a worst case notion in the sense that this works for every input. And this is not an average case notion in this sense. Now, by using this universal heuristic scheme, I can explain this part, which is quite simple. So what I'm going to show you is that if you have a universal heuristic scheme, we are going to show that there is an efficient algorithm that can solve in 2 to the order n by log n. And let me explain why this time complexity appears. So we can prove the following. If we have a universal heuristic scheme for problem L, we can show that L can be solved in slightly faster than 2 to the order n. The proof is quite simple, and I can explain the proof in this one slide. So the basic proof idea is that we can take a parameter t so that the input x becomes computationally shallow, in the sense that the computational depth of x is less than order n by log n. And it's actually easy to prove that there's such a computationally shallow parameter. In order to show that, let's consider the following simple telescoping sum for some parameter capital I, which is order log n. Let's consider t and p of t computational depths of x. Next, let's consider p of t, p of t computational depths of x. And let's continue it until you get p to the I of t. And let's remember that the computational depth is defined as the difference between time-bounded column complexities. So you can cancel out the adjacent terms. Now what remains is the first term and the last term. So the first term is this, and the last term is this. Now remember that the computational depth, the time-bounded column complexity of x is always at the most n. And it's of course non-negative. So we can bound this by n plus order 1. Now, if you take the minimum term among the left-hand side, we can find some parameter I such that the computational depth of x is at most n by I. So we get some time parameter t such that the computational depth becomes at most n by log n. Now, the reason why we get the running algorithm that runs in 2 to the order n by log n is that the universal heuristic scheme runs in 2 to the order n by log n. So this is a reminder of the definition of universal heuristic scheme. So how can we prove it? Well, now we can consider the following algorithm, which we call B. The algorithm B just takes the universal heuristic scheme and you run it for several different parameters t. So you start from some large parameter t, and you simulate it with respect to the time parameter p of t and p square of t and so forth in parallel, and you take the first one that holds and output what it outputs. And the proof of correctness is clear because we require that the universal heuristic scheme is correct for every input. So this algorithm is of course correct. Now what's about the running time? Well, the running time, since we take the first one that holds, we can take the minimum parameter I of the running time of the universal heuristic scheme. So it's going to be 2 to the order computational depth of x plus log of the time parameter. So we have two terms which you need to balance. And if you balance this term, you can find that the parameter of epsilon times log n is the best choice. And we can upper bound this running time by 2 to the order n by log n. So the reason why we get 2 to the order n by log n is that we can find such a computationally shallow parameter. Now I can explain how we can overcome the limits of black box reduction. Remember that in order to bypass the barrier of black box reduction, we need to exploit the efficiency of an oracle. In other words, we need to exploit the efficiency of average case polynomial time, which we assume that it is polynomial time. Now, if we go through these implications, we can show that under these assumptions, we can show that there is a universal heuristic scheme which runs in time 2 to the order computational depth of X. And the parameter in the universal heuristic scheme, which is P prime, comes from the polynomial of the original average case polynomial time. In this way, if the algorithm is indeed efficient, we can prove these implications and in a non-black box way. But if it is not efficient, we can't prove these implications. So in this way, by using this kind of metacompressive proof techniques, we can exploit the efficiency of average case polynomial time, and therefore the proof is not subject to the barrier of Bogdan and Trevisan. So there are several other parts in the proof, but because of the time constraint, I will not explain this, but let me quickly mention how we can prove this. And in order to construct a universal heuristic scheme, there is a notion called the direct product generator, and we combine it with weak symmetry of information. And by using that, we can show that if there is an efficient algorithm that approximates NP oracle time-bounded column complexity, we can construct universal heuristic scheme for every problem in NP. Now, for this part, which connects average case complexity of pH to worst case complexity of NP, metacompressing of NP, we use the notion of direct product generator again. Since we still have a time, let me explain the notion of direct product generator, and let me try to explain how we can prove this kind of implication. So there is a very important tool for analyzing time-bounded column complexity, which we call Kwise direct product generator. The definition of Kwise direct product generator is quite simple. So this is the definition, which is derived by dp sub k. This direct product generator takes an input x as well as a seed z1 up to zk, and the output of the direct product generator is defined as the z1 up to zk and concatenated with the inner product between z1 and x and zk and x. So this is quite a simple definition, but what it is? Well, this is actually a pseudo-random generator construction that is based on a hard truth of x that extends seeds z by k bits. Sorry. What's important about this Kwise direct product generator is that it satisfies the following reconstruction property. We can prove the following for every oracle D and for every input X. Let's say X has high column complexity with respect to D, in the sense that the column complexity for X is greater than K plus order log n. Then we can show that this is a secure pseudo-random generator against D, in the sense that we have the following approximate inequality between two probabilities. The first experiment means that the oracle is given direct product generator, the output of the direct product generator as input, and the second experiment is that you are given the uniformly at random sequence W. And it says that you can't distinguish W from the output of the pseudo-random direct product generator. So what's important about the Kwise direct product generator is that the advice complexity is very tiny. So it's at most K plus order log n, which corresponds to this value. And actually, this is known to be nearly optimal. In the context of, if you are familiar with pseudo-random generator, in the context we usually try to maximize the extension of the seed, but what's important in the context of analyzing time-bounded complexity is to minimize the output so that the advice complexity becomes small. And this tool turned out to be very useful. And let me show you how we can use this notion to get a worst case to average case connection. Namely, let me explain how we can prove that if NP is easy on average, then gap minkety is in P. Let me explain this in this one slide. For simplicity, I'm going to ignore a time parameter and let's fix T to be something like polynomial, n squared or anything. Now let's consider the following distributional problem. So I'm going to take some problem in distributional NP, and I'm going to use that algorithm to show to construct an algorithm for minkety. Now the problem, distributional problem we consider is essentially the minkety problem, but we consider with respect to the uniform distribution. Namely, we pick a uniformly random input to X, and the problem is to decide whether you can compress it by two bits or not. Namely, we want to decide whether Kolmogorov compressed of X is less than n minus 2 or not. Now let A be average case algorithm or equivalently errorless heuristic polynomial time algorithm that solves this distributional problem with high probability. In other words, the algorithm outputs the correct answer or a special symbol bottom, which means the time amount of the heuristic algorithm. In particular, we have the following two properties. If it is yes instance, namely, if the Kolmogorov complexity is smaller than n minus 2, then the algorithm outputs 1 or a time amount symbol. And moreover, if you pick a uniformly at random input, the algorithm time outs with probability less than little order of 1. Now, the reduction that we use is the simplest reduction that you might think of. So here's a randomized algorithm for solving gap minkety. So let's say you are given X and 1 to the S, and you want to decide whether Kolmogorov compression of X is at most S or not. The definition of the reduction is simple. You just take direct product generator and you apply the algorithm A, errorless heuristic algorithm A on the input, and you check whether it is 1 or bottom symbol. And in that case, we output 1. And we do this for a random choice of Z and K, where K is slightly larger parameter than S. Now we need to prove the correctness of this quite simple algorithm. In the yes case, remember that gap minkety yes instance is this. So let's say the input can be compressed to S bit. In that case, we can measure, let's measure, I'm going to claim that B outputs 1 with probability 1. Why is this the case? Well, let's measure the Kolmogorov complexity of direct product generator. Then we can upper bound this by Kolmogorov complexity of X plus the length of the seed. Because in order to compute this string, if we are given a program that prints X as well as a seed Z, we can compute the output of the direct product generator. And we can, if we compute this, we can show that this is at most K plus NK minus 2, which is the length of the output of the direct product generator, which means that this input is an yes instance for the distributional problem. Therefore, since this is a errorless heuristic scheme, this algorithm outputs 1 or bottom symbol with probability 1. Now, the more interesting case is the no case. In this case, we exploit the efficiency of the oracle A. Namely, let's say the time-bounded column compressed of X is significantly greater than S, which is close to K. Now, by using the reconstruction property of the direct product generator or pseudo-randomness of the direct product generator, we can show that the probability that A outputs one or bottom with respect to direct product generator is close to the probability that A outputs one or bottom symbol with respect to the uniform random W. Now, if you pick W uniformly at random, you can show that the column complexity is quite high. In particular, this is violated, so we can show that this is up small. So we conclude that V outputs one with small probability. So in this way, we can prove the correctness. And the reason why this is non-Blackbox reduction is that this time complexity T prime comes from the running time of the algorithm, which we assume that the polynomial. So the message of this slide is that gap MinKT is a metacomputational problem, and by exploiting that this problem asks for the complexity of generating of X, we can develop a non-Blackbox reduction proof techniques. So to conclude, metacompressed is a powerful tool to analyze average complexity, especially because it allows us to overcome the limits of Blackbox reduction. But there are a lot of interesting open questions. One of the important questions is to develop non-relativizing proof techniques in this context. In particular, personally, I believe that there is a NP hardness proof of gap MinKT which doesn't relativize. Thank you so much for your attention. That's
Thank you very much, Shuichi, for the talk that includes a lot of material about your work on this. So let me ask if there are any questions from the audience here or from the remote audience. Yeah, so one thing I would like to ask is, so all the results that you presented are for uniform complexity. And so sort of in crypto, it's often convenient to think about the adversaries as being non-uniform. So for example, if I want to start with some problem which is outside CoNP, which is worst case hard, can I get average case hardness against non-uniform adversaries, say if I assume uniform hardness against circuits also?
Yeah, that's a good question. Unfortunately, currently, no.
So this only works for even if I don't start with KT, but if I start with some other hard problem that's about circuits, then I cannot get any hardness results against circuits, or no?
Yeah, basically we need to exploit the efficiency uniform algorithm. But let me mention that if we consider MCSP, gap MCSP, yes, we can construct a non-uniform worst case to average case reduction.
So you can. So if we assume that MCSP is hard for circuits, yeah, then you get average case gap version is also hard for circuits.
Right. Okay. If we assume that gap MCSP is hard in the worst case, then MCSP is hard on average, right, with respect to uniform side. Yeah.
And this results sort of, if I assume concrete hardness of problems like MinKT or MCSP, sort of, I mean, the results you presented here, sort of, you have to start with exponential hardness to only, like in the worst case, to only get like polynomial hardness in the average case, right? But say if I start with the assumption that MinKT is exponentially hard in the worst case, do I get exponential hardness in the average case too?
Yeah, for let me think. Yeah, I guess so. Because for MinKT, we can basically, yeah, in the case of MinKT, basically the worst case complexity and the average case complexity are equivalent. in some technical sense. So if we assume that gap minkate is exponentially hard, if and only if minkate is hard, exponentially hard on average. But one thing I should note is that the time complexity becomes larger, so the gap between yes and no instances becomes larger in the sense that T prime becomes large. But yeah, it's possible.
Okay, thanks. Any other questions? Okay, so maybe I can ask one more question about something that sort of, I guess I didn't get this part, but I remember that your initial paper, you didn't use this direct product generator, but you used the Nissan-Wigderson generator. So yeah. Why is this better? Or is it just better? So this part I did not get. Is this better just for this specific reduction, or is it sort of, does it always give you better parameters?
This basically always gives a better parameter, because if you use Nissan-Wigderson generator, the advice complexity isn't optimal. Yeah, for this, basically the gap of yes instances and no instances comes from the advice complexity. And
so here in the reconstruction, you need to use less advice to do.
Yeah, this is the least advice that you can get, and the advice is this. So in some sense, this is optimal, and this optimality goes to the gap between yes instances and no instances. So here the gap is just additive order of n, and this comes from the optimality of direct product generator.
Okay, thank you. Well, let's thank Shuichi again. Thanks a lot for coming to the workshop and for giving the talk. And we continue tomorrow at